Hello everyone, my name is Jason Gregerson, and welcome to the next video in your Calculus 2 video set. This is the second video on section 7.2, trig integrals. Recall from the last video that the big idea of 7.2 is how do we integrate integrals that contain trigonometric functions. In the last video, we discussed the first two techniques where we simplified the integrand using either just converting things to sines and cosines or using trig identities. In this video, we want to talk about using substitution to do some of these integrals, and then also maybe simplifying with some trig identities first, and then using substitution. So without further ado, let's get started. Alright, so here we have our first integral, the integral of cosine of x sine squared of x. And the idea is, if you recall the process of substitution, we're looking for integrals that have this general form. And the big idea was that there was some inside function whose derivative was a factor. And that was the big signal that substitution might be the appropriate technique. In this integral, I have that situation. I have a function sine of x that's being acted on by another function is being squared. But the derivative of sine is equal to cosine, and so I have that derivative is a factor. That tells me substitution should be appropriate, and that I want to let u equal that inside function, sine of x. And if I just took that value and I plugged it into my integral, I would replace the sine squared piece now with u squared. However, I still got to take care of the cosine of x and dx. But if u is equal to sine of x, I can write its differential, du, as the derivative of sine, which is cosine, times dx. So that's the differential du. So now I see that I can replace cosine of x dx with what it's equal to, which is just du. Now I've made this integral much simpler. I can integrate this to get u cubed over 3. And then if I convert everything back to x's, I can see that the integral of cosine of x times sine squared of x dx is just equal to 1/3 sine cubed of x. And so there's my solution. Now a couple big ideas here. The substitution u equals sine of x is replacing all the sine pieces. So it actually really doesn't matter if this part was maybe more complicated in terms of sines, because I would just replace all those sines with u's. However, because the differential has the form cosine of x dx, this cosine has to be just cosine raised to the first power. It really can't be any more complicated. So having that single factor cosine of x is really important for being able to do this substitution. Alright, let's take those ideas and extend it to a little bit more complicated problems. So here, once again, we want to use that same substitution. We're going to let u equal sine of x, and then the differential du will be cosine of x dx. And once again, we were tipped off because we had the single factor of cosine of x here. And now when we put these u values into our integral, we can see that even though this is more complicated than before, when we replace the signs with u's, this just turns into u cubed minus 2 times u. And so really, even though that part was more complicated, it just resulted in a polynomial in terms of u, which is relatively easy to integrate. And then I have my single factor of cosine with the dx, and so I can see that's equal to just du. And now I can integrate this, u to the 4th over 4 minus u squared. And then lastly, I can put in my x pieces here, which will be 1/4 sine to the 4th of x minus sine squared of x, plus my integrating factor. So I can see that even though that was more complicated in terms of the sine pieces, it really didn't slow me down when I wanted to use substitution. Now the next integral demonstrates that I can also do it with the opposite substitution here. Instead of u equals sine of x, I could also let u equal cosine of x. Now why am I switching it here? Well, if I let u equal cosine of x, then du should be the derivative of cosine, which is negative sine of x. Don't forget that negative. And if I multiply both sides by -1, I can say negative du is equal to sine of x dx. So really to make this substitution work, I would need a single factor of sine. And I can see that over here in my integrand. So you're really looking for which piece has that single factor here, where just sine or cosine raised to the first power. And that tells you that the other piece be your substitution. So I plug these values in, and once again I'm replacing all the cosines with u's, so it doesn't really matter how complicated that is. U squared plus 4 u to the fifth power, and then that sine of x dx gets replaced by negative times du. And now once again, I just have a polynomial in u. I integrate this using power rules and plug in my x's again, and I'm done. So that really hits the big idea of using substitution to work on these integrals with trigonometric functions. But once again, the big restriction was that I had to have this cosine of x to the first power, or the sine of x to the first power. So what do I do if I don't have one of those pieces? Let's look at the next technique. Okay, so now I have this more complicated problem. I have cosine cubed and sine squared. So I can't just start off and do my substitution because I don't have that single factor of sine or single factor of cosine. But what I can do is use one of my trig identities to help put me in that situation. If I look at my trig identities up here, the first one, the Pythagorean identity here, relates sine squared to cosine squared. So it will let me go back and forth for these even powers of sine or cosine. But here I have cosine cubed. But I could rewrite cosine cubed to be cosine of x times cosine squared of x. So I've taken out that single factor of cosine that I want. So now I have the single factor of cosine that I want to be able to do my substitution. What else do I need my substitution? Well, I'd prefer to have everything else in terms of sine. So now I can use that Pythagorean identity to convert the cosine squared to a sine squared. And so if sine squared plus cosine squared equals 1, we saw in the last video that oftentimes I'll want to maybe solve that for cosine squared to say cosine squared of theta is equal to 1 minus sine squared of theta. And that's the piece I'm going to use here. I'm going to write this as cosine of x times 1 minus sine squared of x times sine squared of x dx. So now I have my single factor of cosine and a whole bunch of stuff in terms of sines. And remember, I don't care how complicated that sine stuff looks like because that will be taken care of with my substitution. So now I know I can let u equal sine of x. The differential then will be cosine of x dx. And when I plug these values into my integral, well, all that sine stuff simplifies nicely. And cosine of x dx is just equal to du. And once again, I've simplified this now to just a polynomial in u. So in fact, let's just finish this up by distributing that u squared to get u squared minus u to the fourth du, integrating to get u cubed over 3, u to the fifth over 5, and then replacing our u's with sine of x to get 1/3 sine cubed of x minus 1/5 sine to the fifth power of x, and then don't forget that constant of integration. And so there's my antiderivative there. So that quick summary is just when you have this odd factor of either cosine or sine, you can pull out a single factor and then convert all the even powers over to the other trig function using that Pythagorean identity. Let's look at another example. Here we have cosine to the fourth times sine to the seventh here. And so now I am seeing that I have an odd power of sine instead of cosine. So I could rewrite this one as cosine to the fourth of x times sine to the sixth power of x times that extra factor of sine of x. So once again, we've been able to identify a single factor of either sine or cosine. I'm going to need that for my substitution. And now I just need to convert this sine to the sixth power over to cosines. Well, this might be a little more complicated because I don't have just sine squared, but I can rewrite this as sine squared of x raised to a certain power, right? I can raise it to the third power times my extra factor of sine of x dx. Now I can just go ahead and use my Pythagorean identity to replace this 1 minus cosine squared of x. That's all cubed sine of x dx. And once again, I have complicated stuff in terms of cosine, but that's okay. Single factor of sine. Now I can let u equal cosine of x, and then du should equal negative sine of x dx. Multiply both sides through by -1, just moves the negative sign over here. Plugging in all my u values gives me u to the fourth 1 minus u squared quantity cubed. And then I replace the sine of x dx with negative 1 times du. And this might look a little bit complicated, but really, once I expand everything out, I'm just going to get a big polynomial in u. Just integrate using the power rules, and then I convert back to x's. So it's really not that bad of a problem to finish up with. One last problem I want to look at. This one's cosine to the 5th power. And this one might look a little confusing at first, like, wait a second, I don't even have any sines in this one. But it actually doesn't matter. I can still use that same approach. So in this one, I'm just going to pull out that single factor of x again. Now I have cosine of x times cosine to the 4th power of x. And I'm going to do the same thing. I'm just going to convert cosine to the 4th over to sines. It doesn't really matter that I don't have any extra sine pieces. This is still a useful technique for integrating something where we have an odd power of one of the trig functions. So just to finish this up, let's just say we have the integral of cosine of x, and now we have cosine squared of x, quantity squared. And then this will be the integral of cosine of x. We'll use our Pythagorean identity. This is 1 minus sine squared of x, quantity squared. And now I'm ready to make my substitution. Let u equal sine of x, that's the complicated stuff. And then du, the differential, will be the derivative of sine dx. And so plugging all this stuff in, I get 1 minus u squared, quantity squared, du. Once again, expand this, integrate the polynomial, replace everything with x's, and then you're all set. In conclusion, section 7.2, we talked about how to deal with integrals that contain trigonometric functions. We had our 4 big strategies. The first video covered how to convert everything to sines and cosines. Sometimes that was all you had to do to make it easier. Sometimes we had to use some trig identities. And then today in this video we saw how we can use substitution for some integrals. And also sometimes we had to prepare the integral using some trig identities, and then we were able to use substitution. Alright, so that concludes this video. Thanks for your time.